Okay, now what we're going to talk about now is the so-called torsion equation. Okay, so I'm going to talk about this torsion formula. And I'm just going to write it up there to begin with, and then we'll derive it, just to see what we get. The point of this video is to get the torsion equation. This is really important. This is basically P of A for torsion. The actual equation is as follows. The shear stress is equal to the internal reaction torque, T, that's T at a cross section, times the radial distance over this geometric quantity called J. Right? So we're going to derive this in a second. So this relates the internal force, the internal reaction torque, to the shear stress. So that's just like sigma equals force over area. Think about it. For axial, we were worried about the axial, the normal stress sigma. Here we're worried about the shear stress value. In the axial, it was related to the internal reaction force, the axial internal reaction force, P. Here it's the internal reaction torque, T. Again, don't use some external torque. It might be the situation that the internal is equal to the external, but that's not always the case. The stress arises always from the internal reaction forces, not the external forces that happen to be sort of close to it. Okay, now when we talk about the axial stress, it's divided by the cross-sectional area. That's the geometric factor. Only has to do with geometry. In torsion, J is basically the geometric factor that we're interested in. Usually we just call it J. Everyone knows it. But J is really what we call the second polar area moment. When you take dynamics, you'll actually have a second, you actually use J as well, but it's the moment of the mass, not the area. Second, we'll show you where it comes from because it's the second moment that has a squared in it. And polar because it's integral with respect to the radius. You'll see that once we derive it. Now, the last thing is it has this little different wrinkle that the radius goes in. So this makes sense because from the last video we showed that, the last video, that shear strain increases as we move out from the radius, linearly proportional to the radius rho. It goes to 0 here, and it's the maximum value out here. Now, if the shear stress is proportional to the shear strain through the modulus rho G, the shear modulus G, then obviously the shear stress has the same type of distribution. So the shear stress is 0 at the center line. No matter what's going on, it's always going to be 0 here. It increases linearly its maximum value on the outer surface, and that maximum value would be internal reaction torque times the outer radius over this geometric factor. Okay. This you have to memorize this. P over A, everyone knows that. You'll also have to know T rho on J or something. All right. Where did that come from? Well, we already, just to review really quickly on the kinematics, what's going on here, right? We put a torque on here, T. Each one of these disks rigidly rotates. As you move down in X, you get more rotation. That's the angle phi, right? Phi is a measure of how much each one of these disks rotates relative to the disk back in base. Now doing that, we can get the relationship between the shear angle, gamma, the one that causes the actual shear strain, and how much phi changes with respect to X. But basically, the important thing to recognize is that gamma varies linearly with rho. All right, so if gamma varies linearly with rho, then obviously the stress has to vary. So basically, tau is equal to G times gamma. We know that gamma is going to be basically, well, we know that gamma is rho dp dx. All right. Now we don't always know what dp dx is. That's kind of not a measured quantity initially, but basically we can also write this as gamma equal to the max gamma times rho over c. So, where does that come from? Well, gamma max is the shear strain at the outer radius, and we know it's linearly proportional to rho. There's a maximum value when rho equals c. So when rho equals c, this goes to 1. Otherwise, it goes to 0. So the shear strain vanishes here, increases linearly, gets its maximum value. So we can just rewrite this as well. Right? So again, the shear stress is got the same relationship. All right. Now, if that's the case, I can just do a little more. Well, if you like algebra, let's just work on the algebra a little bit more. So now, tau equal to G times the maximum, oops, you can't see that, sorry. G times the maximum shear strain. That is actually going to be the maximum shear stress, tau max, right? And again, that happens in the outer radius. So this is just going to be tau max times rho over c, all right? And that's what you're seeing here, SE, right? The shear stress, tau, is 0, at rho equal to 0, increases linearly until you get out to the outer radius C, where the shear stress equals tau max. So right here, right? As rho goes to C, you get tau max. So rho equals 0, the shear stress goes to 0. And don't forget this little visualization cube here, especially when you combine loading later on in chapter 7. It's nice to be able to visualize how those forces are acting on the face. So if you look at this, this is the little adifferential cube. You can see the plane in which that shear is acting is actually this plane, right? That's the plane that's seeing the shear stress. So if you think about it, this is the x direction. This is the radial direction. And this, well, the way, and this orientation, this would be, this is the line of the x-axis, and this is the line of the y-axis. So in this orientation, it would be tau x, I'm sorry, this would be the tau of x twice. This is definitely x, this is y, right? This z. So, excuse me, so this is the y direction, and this is the z direction. So this is tau in the y z direction. So that's the component of the shear stress. Now, if you look up here, right, the shear stress occurs in shear stress occurs in this plane. Okay? That's the plane that the square becomes a form trapezoid, right? Okay. So if that's the case, then this shear stress here is tau y x plus tau y okay? Gamma tau x y. Right? So changes where it is on the circle. Actually, always, you can always consider this always to be radial direction, and this to be the phase direction, so it's actually always required phase. But we have no choice. But, you know, I probably shouldn't have too much into the letters, but don't worry about it too much. Be able to visualize the shear point. Okay? Be able to visualize the shear point. Okay. All right. The stress is 0, varies out to the maximum at the outer point. Okay. And here's another picture that kind of shows the visualization. Right? See we have a shear stress component on this face, but we also have to balance it on this face. Okay. Now what I want to do is if you look at this, I'll show it better on here. If you look at, say, let's just pick this one, okay? Each one of these little differential areas has a differential force associated with it. So here's a differential force here. Okay? Now that differential force is a distance rho from the center. So it produces a differential torque or a moment around this center line. So you have to imagine this pinwheel stress distribution. Each one of these little squares induces a small torque, okay, around the center line. The integral of that over the whole face has to equal the internal reaction torque. That is the one that gives you this internal reaction torque. Remember, just like in the axial problems, there is not like an internal reaction force at the center. It's a way we abstract the actual complex stress distribution. So what's going on here is there is this idealized stress distribution, pinwheel stress distribution. We want to figure out the net torque resulting from that. That's the internal reaction torque, T, okay? That's going to allow us to rate tau for T. Okay, so we're going to do that. That's what I'm going to do next, okay? So let me just pause and restate that here. It's a little more clear. We want to relate tau max, to the internal reaction torque T. So this internal reaction torque, again, is fictitious, but it's what we use to describe the net effect that each one of these little stress cubes here induces a torque around the x-axis. Okay? All right, so let's do that. Let's keep that picture up here. Keep that up. Keep that there. So, what I'm saying is, internal reaction torque, T, has to equal the integral over this face, this cross-sectional face here, A, of the differential torques of all these little cubes, right? Now this differential torque is going to be dF times its moment, rho. Now dF, the magnitude of this, is going to be the shear stress, tau, that's force per area, times the differential area, dA. This right here. Right? That is dA. Okay? So put that all in, you get that. This now becomes the integral over the cross-sectional area of just rewriting stuff. Rho tau dA. Okay? All right. That doesn't really help things yet, but we're almost there. All right. So remember, tau varies. It doesn't vary as a function of theta, but it varies as a function of radius. We already talked about that somewhere, right? Right here. Remember? Varies linearly as a function of radius. So tau is really, you should write this as tau rho, right? Here. This is tau rho. Now, the way the shear stress is related to the radial distance, we can use this assumption that it varies linearly. It comes from the kinematic assumption of the strain variable. So if we put in for here, tau max times rho over c. Now what do we have? Now we have that the internal reaction torque, T, equal to the integral over the cross-sectional area of tau max, the maximum shear stress of the outer radius, rho squared over c. C is the outer radius. All right. Now, tau max and c are constant. They're not a function of position. C is the outer radius. That's the outer radius regardless of where you are. Likewise, tau max is the same regardless of whether you're here or here. Tau changes, but tau max is the same. So I can pull those out of the integral. So now I have tau max over c integral rho. I'm sorry, integral over a rho squared dA. All right. So we don't like integrals that much, right? Nobody's a big fan of integrals except some mathematicians out there. So we don't like to deal with it at this point. But if you look at this quantity here, that only involves geometry, right? It doesn't involve the stress, it doesn't involve loading. It's purely a function of the shape, right? It's basically an integral of the radius, right? You know, for example, we just talked about the integral of a dA. That's the area, right? It's only geometry. Now, if we talk about the integral of rho dA, okay? This actually, you can see, like, divide this by the area. That gives us this location of the central, right? In this case, 0. But this is what we would call the first moment. First area. So this is the zero area. That's simply just the area, zero area. It's basically, you can imagine, this has got a rho to the zero. Rho to the zero. Right? Rho to the zero is just 1. Zero area moment. Here's the first moment. This involves rho. And now what we have up here is the second area moment because it involves not rho, but rho squared. So this is the second area moment. Now it's in polar coordinates, so we call it the second polar area moment or something like that, right? All these are probably polar. Well, when we do bending, we'll have ones that are for the Cartesian axis, not polar axis. And if you took dynamics, or you're going to take dynamics, you'll see something very similar, but this won't be dA, that'll be dm, so it's not an area moment, but a mass moment, okay? But that's where they come from, so we call that. But, you know, if you ask a group of mechanical engineers and you say J, pretty much everybody knows what you're talking about. That is the J. You talk to electrical engineers. Mechanical engineers, J, most often, you know, that second polar area moment. If it's only geometry, it has nothing to do with the load, it's only a function of geometry. It acts the same as A does in the axial stress thing. So let's just leave it that way. We're going to call it J for now. You can calculate it for various cross sections, but you can also look them up. You can see these things are tabulated. Actually, here it's not tabulated, but later on we'll show that. J is actually the sum of these two lines. They're in tables. Right? So we're trying to relate the internal reaction torque to the stresses. Put in the linear stress distribution assumption. Now we have all this. Internal reaction torque T equal to tau max. That's the maximum shear stress at the outer radius okay, on this surface, over C, that's the outer radius, times this geometric quantity J. Just going to leave it like that for now, because we can figure out J, initially. All right. Let's get the stress. Let's isolate the stress, because that's what we're interested in. So now we have the maximum shear stress, the stress of the outer surface, is equal to the internal reaction torque T times the outer radius C over J. All right? So that is one form of the torsion equation, torsion formula. Okay? This is saying, I know the cross-sectional geometry, I can compute J, I know the radius, C. Now I can relate the internal reaction torque to the maximum shear stress, okay? To the maximum shear stress, all right? So that's a really useful design equation. You definitely have to memorize that. That's one form that's close to what we have here. Now, this is only giving you the maximum shear stress. You can also get the shear stress as a function of position. So we know that tau max, well, you know that here, tau max rho over C. So tau max is tau times C over rho. Tau times C over rho, right? So this gives me tau C over rho, T C on J, C's cancel out. Let's multiply both sides by rho. Now we have tau equal to T rho on J. That really is probably, this really is the torsion equation. That's the one you should probably memorize. That makes sense. Again, this actually gives you the stress all throughout the cross-section as a function of radius. But if that outer radius, I'm sorry, if rho becomes the outer radius, that's where you get the maximum shear stress, right? The outer surface. So that's when rho equals C. When rho equals C, you get this equation. This equation, tau. Okay? Torsion equation. Really important. Again, I know we went through the derivation. It's not that hard of a derivation, but it's interval and whatever. But let's pause and review kind of the physical significance of what's going on. Okay, where's the... Oops, oh. Okay. Okay, this one's not. This is right? Oh, here. We know that the shear stress varies linearly. The max is at the outer surface. Each one of these little differential shear stresses produces a differential torque. The sum of those, or the integral of those, equal this internal reaction force, this idealized internal reaction force. Okay? So you can figure these out from free body diagrams, right? You take the cross section, you figure out the internal reaction force, just like you do in the axial flux. We know the geometry, so that gives us the ability to compute shear stress in the component under torsion related to geometry, J and C, and the internal reaction torque, T, which comes about from free body. Okay? All right. And so T goes bigger, stress goes bigger, J becomes bigger, geometry becomes bigger, that the stress goes down. But also, don't forget, stress varies as a function of the radius. Unlike with axial stress, where the stress is uniform over the cross-section, there's a dependency on rho. Okay? All right? I'm going to break here. I was going to talk about J, but I think I'll put that in